Ever bitten into something really hard, maybe, a tough pretzel or something, and just for a second, worried your tooth might actually chip. And then it doesn't. Your teeth just sort of take it. It's pretty amazing when you stop and think about the incredible forces they handle day in, day out for decades. But what if the secret to building super strong, really durable metal parts for things like, say, an airplane or maybe a medical implant was hidden right there inside your mouth? Today, we're doing a deep dive into some really groundbreaking research. It's literally taking inspiration from your tooth enamel to create metals that aren't just tougher or more resilient, but also, surprisingly, corrosion-proof. So get ready for some serious aha moments, because we're about to unpack how nature's amazing design could actually revolutionize engineering. Okay, let's get into this. Metals. They're the backbone of modern engineering, no doubt, everywhere. Cars, planes, bridges, even our phones. They're strong, versatile, fantastic stuff. But even the best ones, they have some, let's say, inherent weaknesses. What are the big headaches that engineers are constantly wrestling with here?
Yeah, what's really fascinating is that even our most advanced engineering metals, the ones we count on in really extreme conditions, think inside a jet engine or parts for a nuclear reactor, maybe a deep sea vehicle, they always involve trade-offs. Big ones. It's kind of a constant balancing act. If you push to make a metal incredibly stiff and hard, which sounds good for strength, right?
Right.
Well, it often gets brittle. It loses its ability to absorb impact energy, what we call its damping capacity. So a sudden shock and bam, it could crack or shatter, a bit like dropping a ceramic plate.
Okay, I see.
And then you've got other challenges. Metals are generally heavy, which limits their specific mechanical performance, basically, their strength for their weight. That's huge for things like aerospace, where every single gram matters. And of course, the big one, corrosion. Saltwater, harsh chemicals, even just the air around us, it slowly eats away at metals. This doesn't just cut down their lifespan, it costs billions in maintenance. And I mean, it can be catastrophic if a critical part fails because of it.
So, yeah, these aren't minor issues. They're fundamental limits engineers have been trying to crack for a long, long time. What have been the usual ways to try and fix this? And why haven't they totally solved the problem?
Exactly. And engineers have tried a lot. Complex alloys, these newer high-entropy alloys, advanced 3D printing for intricate shapes, metal ceramic composites, applying all sorts of protective coatings. Each approach has its benefits, sure, but they all come with compromises. You might get an alloy that's super stiff, but maybe it doesn't have the damping you need for vibrations.
Okay.
Or you put on a ceramic coating that's great against corrosion, but it adds weight. Or even worse, it makes the whole thing more brittle. If that coating cracks, the whole structure could fail catastrophically. So the real goal, the sort of holy grail, has been to boost multiple properties all at once, strength, damping, and corrosion resistance, without making it heavier or creating new weak spots. It's been really tough.
And this is where it gets really cool. What if the answer isn't in some, futuristic lab with crazy new alloys, but in something we all have right now, something that handles incredible forces every single day for years without falling apart?
Precisely. It really shows you how brilliant evolution is. Living things have spent millions of years refining materials that often blow away anything we can make artificially. And one of the most amazing examples, one we probably don't think about much, is tooth enamel, your teeth's outer layer. It's only a few millimeters thick, and get this, it's about 96% ceramic, hydroxapatite specifically.
Yeah, 96% ceramic. But ceramics are usually brittle, right? Like you said, drop a plate.
Exactly. That's my experience too. So how does enamel, being mostly ceramic, manage to be so incredibly tough?
Yeah.
That's the wow moment. Despite being mostly brittle ceramic, tooth enamel combines amazing hardness and stiffness with really substantial damping. It resists cracks, absorbs energy. That's how it lasts maybe 60 years or more in your mouth. Which is, let's face it, a pretty challenging place. Wet, chemically active, acids, temperature changes, huge chewing forces. It's a masterpiece of material design.
Okay, so what's the secret sauce then?
It's all about the structure. It's this incredible hierarchical arrangement. Imagine millions of tiny, tiny ceramic nanorods all lined up. But they're not just packed rigidly side by side. In between them, there's this amorphous intergranular phase, AIP. Think of it like a non-crystalline sort of energy-absorbing glue filling the tiny gaps. Amorphous means its atoms aren't in a perfect repeating pattern like the ceramic rods. It's more disordered, almost like a super dense gel or maybe a shock-absorbing polymer, but at the nanoscale.
Okay, like a cushion between the hard bits.
Exactly. That glue provides flexibility and toughness. It absorbs energy and stops cracks from just racing straight through. So instead of shattering, a crack hits this interface, gets slowed down, maybe diverted,
Yeah.
it keeps the whole thing intact. That's what makes enamel so durable. It's totally unlike what you'd expect from a standard ceramic material.
That is genuinely mind-blowing. It's not just strong, it's smart about handling stress.
Mm-hmm.
So,
Okay.
okay, how do we use this? How do we take that natural design, this enamel superpower, and apply it to, I don't know, metal for a jet engine part, or a car door, or an implant? That feels like a huge jump.
Well, that's precisely the challenge. And honestly, the genius of the research we're talking about today. It's about taking nature's blueprint and translating it into real-world engineering. The team leading this, folks like Xiaoji Liu, Jinjing Deng, Hui Zhao, and Ling Guo, with major contributions from Robert O. Ritchie, and others published their work in a top journal, Nature Communications. These researchers, they come from places like Beihang University, Peking University Health Science Center, and also the University of California, Berkeley. They developed what they call an enamel-inspired ceramic coating, or EIC. They didn't try to invent something totally new from scratch. They looked closely at the tooth, figured out the principles, and then found a way to apply those principles onto metal surfaces. They started specifically with zirconium foil, ZR foil. That's a metal already used in tough spots like nuclear reactors because it's strong and resists corrosion pretty well. Their goal was to build that enamel-like structure right on top of it.
Okay, so how'd they do it? How do you build something like that on metal? It doesn't sound like you can just paint it on. Was it super complicated, like lasers and vacuums?
Surprisingly, no. That's another really neat part. It's sophisticated, for sure, but the method itself is described as a relatively simple wet chemical process. Imagine growing tiny, vertically aligned ceramic nanograss made of zirconia, ZRO, directly onto the metal. Think of it like blades of grass, but incredibly tiny, mimicking those enamel nanorods.
Nanograss, okay.
They use techniques like hydrothermal growth, which is kind of like how crystals form in hot springs, using hot water solutions, but done with extreme nanoscale control. And then controlled hydrolysis. Then the really clever part. They carefully filled in the tiny spaces between those nanograss blades with a non-crystalline amorphous version of the same material, ZRO. This perfectly mimics the crystalline rods and that amorphous glue of real enamel. Creates that shock-absorbing network right there on the metal. It's really elegant nanoscale architecture using chemistry.
All right, nanograss and amorphous glue. They built it. That's amazing in itself.
Yeah.
Did it work? What kind of superpowers did this new ZREIC metal actually get?
The results were, frankly, remarkable. The ZREIC showed what's called a viscoelastic figure of merit, or VFOM, of 4.6 GPa.
Okay, 4.6 GPa. Is that good?
Good! It's phenomenal. To give you some perspective, this was the highest value ever recorded for any metal at room temperature, about 7.6 times higher than typical engineering materials, which are usually down around 0.6 GPa.
Whoa, 7.6 times higher. That's not just better, that's a whole different league.
Exactly. It's groundbreaking because it means they achieve this incredible balance of stiffness and damping. It's super strong and rigid, but, and this is crucial, it can also absorb impacts and vibrations without breaking.
That really changes things. Because engineers usually have to choose, right? Stiff means brittle, flexible means maybe not strong enough. This sounds like the best of both worlds. What about corrosion? Did it help with that too?
Yeah, it absolutely did. Connecting back to that major problem, this enamel coating showed exceptional resistance to salt corrosion. They did a standard neutral salt spray test, basically simulating harsh, salty environments. And the ZREIC. It had a mass loss rate 7 times lower than the plain zirconium foil. It lasted way, way longer without significant damage.
7 times lower.
Yeah.
How does it do that?
The coating acts kind of like a zigzag maze at the nanoscale. It's this tiny labyrinth that makes it really hard for corrosive things like chloride ions from salt to actually reach the metal underneath. It's much smarter than just a barrier. It actively slows them down. So you get this dual benefit, the fantastic mechanical properties and amazing corrosion resistance. It comes from that structure, the stiff nanorods give support, and those interfaces between the crystalline rods and the amorphous glue dissipate energy, stop cracks, and block corrosive ions. And critically, this is really important. The process didn't make the underlying metal brittle. It kept its original ductility, its ability to bend a bit without snapping. That's a huge win over traditional ceramic coatings, which often make things more fragile overall.
Okay, that's fantastic for zirconium, definitely. But zirconium is kind of specialized.
Yeah.
What about other metals we use more often? Does this enamel power work on them too? Could this tech actually change things on a bigger scale, beyond niche applications?
Yes, and this is where the universality of this approach gets really exciting. The researchers didn't stop at zirconium. They successfully applied similar enamel-inspired ceramic layers onto titanium, zinc, and copper substrates too.
Oh, now you're talking titanium, zinc, copper. Those are everywhere.
Absolutely. These metals are vital. Think about titanium tie, crucial for medical implants because it's biocompatible. Well, the tie showed excellent specific modulus and hardness, super strong for its weight. Imagine hip replacements, dental implants that are not only strong but potentially last much longer inside the body. The researchers actually confirmed good biocompatibility for both ZR-EIC and tie-EIC, which is really promising for clinical use.
Okay, that's huge for medicine. What about zinc and copper?
For zinc, which is often used to galvanize steel to prevent rust, imagine much, much better corrosion protection. Buildings, bridges, cars lasting longer. And copper, essential for electronics and wiring. This could mean more durable components, less likely to fail from physical stress or in tough environments. Think more reliable devices, better infrastructure.
So if I'm following this, we could be looking at phones and laptops that don't scratch or dent as easily, cars that resist rust and dings way better, medical implants that are stronger and safer. That feels like it could touch almost everything.
That's the potential, yes. It's quite profound.
But okay, reality check. Even if the chemistry is simple, what are the big hurdles to actually getting this into mass production, making it on a large scale?
That's a very fair question. You've hit on the key challenges. While the basic chemistry might be accessible, scaling it up is a different beast. The process for each metal needs really precise control chemicals, temperatures, reaction times, all at the nanoscale. Taking that from making small foil samples in a lab to coating, say, a whole car panel reliably and affordably on an assembly line, that's a significant engineering and manufacturing leap.
Right, lab scale versus factory scale. Always tricky.
Definitely. And there's the coating thickness, too. It's very thin, around 100 to 270 nanometers. That's great for keeping things lightweight, and it clearly provides amazing protection. But for situations with really heavy wear and tear, extreme abrasion, you might need thicker layers. And the challenge there is to make them thicker while keeping that special enamel-like structure and all its benefits. So yes, there are hurdles, but the research shows a clear path and the potential payoff is enormous. So just to kind of wrap up the key takeaways from our dive today. First, nature's specifically tooth enamel gives us this incredible blueprint for making advanced materials that can beat those old trade-offs. Second, this enamel-inspired ceramic, the EIC coating developed by Liu, Deng, Zhao, Guo, Ritchie, and their colleagues, it simultaneously boosts mechanical strength, stiffness, hardness, damping, and corrosion resistance in really important metals like Zir, T, Zn, and Q. And third, this breakthrough published in Nature Communications has huge potential. We're talking aerospace, military gear, maybe even everyday products, and definitely bioengineering, like those medical implants.
Wow. Yeah, this deep dive really shows how looking closely at the natural world, even something as familiar as a tooth, can spark solutions for some really tough engineering problems. Creating materials that aren't just stronger, but, well, smarter. It really makes you wonder, doesn't it? As we keep pushing the limits of material science, looking everywhere for the next big thing, what other everyday biological superpowers are hiding in plain sight, just waiting for us to figure them out?